This lecture segment goes into a high level, or at least medium level, discussion of how files, directories, and things called inodes are organized in a Unix file system. Now, these subjects are things you would explore more deeply in a course on operating systems, but in a course that deals, at least at the user or programming level, with system calls that relate to files and directories and so forth, a little bit of a deeper explanation is warranted. So let's start by discussing what we mean by file system. I've got a kind of abstract diagram here, and let me detail a little bit what is meant by that. When you store files on a disk, you organize the disk in what are called file systems. A disk by itself is just a large set of data blocks, not even something that one can address byte by byte. Instead, because of the way the disk hardware works, you can get information from it in blocks, perhaps 8 kbytes at a time. But at the hardware level, it's a large body of 8 kbyte blocks, and nothing more than that. No files, no directories, no file metadata, nothing like that. What one does then when you set up a Unix operating system is take either the entire disk or some partition of the disk, a subset of the area on the disk, and organize it as a file system. And a file system has files and directories on it, but it's a little more complicated than that. The diagram here shows two major pieces of information in the file system. These guys right here are inodes. And so a file system area on a disk has an array, for all intents and purposes, stored on the disk, an array of what are called inodes. And these are small blocks of data, perhaps several dozens of bytes long, that give file metadata. When we've been doing fstat and lstat calls earlier on, it has been inodes that were fetched with the content of the inode used to fill in the struct stat that we looked at. So an expansion of an inode might look like this, and this is only part of what would be in an inode. It's more of an example than it is a complete list. But the time at which the file was created, last modified, permissions or mode for the file, the type of file, is it a directory or a standard file or a couple of other special kinds of files we'll mention in a minute. All of that file metadata then is in an inode, which is one of this array of inodes that's the first portion of the file system that is stored on a disk. Now, there is more information in an inode than is obvious from an fstat or an lstat call. One of the most important pieces of information is a set of pointers that lead to where the data for the file is stored. So the file's actual content is the other major part of the file system, and I've represented that abstractly as a series of blocks here, data blocks. The term block on disk means a retrievable unit of information. As I was mentioning earlier, 8 kbytes might be typical. You cannot get just a particular byte from the disk. You need to get data in larger blocks than that. So any file's data will be stored in one or more data blocks, depending on how long the file is. And the location of those data blocks is in the inode. So the inode is sort of your one-stop piece of information about the entire file. Not just the metadata, but also pointers, indexes into the disk, really, that say where the blocks of data containing the file's information reside. Now, a couple of things about those blocks. Nothing says that the blocks of data comprising a file have to be right next to each other. If your file is less than, say, 8 kbytes, then it would all fit in one block, and that would be it. It would just have one block of data. And by the way, if it needs less than 8 kbytes, then typically the latter portion of the block is simply wasted. If it needed more than that, it might require 2 or 3 or 4 blocks of data, but they wouldn't necessarily be contiguous on the disk. They could be scattered all around. I haven't drawn the rest of the file system out here, but these are more blocks down here, and the file might be, say, in this block here, and another one down here, and another one down there. All of that pointed to from an array of block pointers in the inode. Now, the inode is of limited size. It doesn't grow beyond a certain fixed size, really. So it has only so many block pointers in it. And this opens the interesting question of, well, okay, what if the file is really big, a gigabyte file, some movie or something like that? It might comprise many thousands of blocks. How do we have the pointers to all those blocks in a relatively small inode? And the answer is this gets more and more elaborate the deeper you get into operating system design, but a very short answer to a question like that would be, when a file gets large enough, what happens instead is that the blocks that the inode point to in turn have block pointers in them that point to yet other blocks, and we get a sort of tree-like arrangement where there are blocks in the on the disk that are comprised entirely of block pointers to yet other blocks, and you can, with such an arrangement, get an explosively large number of blocks in a file with just one or two levels. Again, that's a broad overview. You're not expected to understand it in great detail, but you will if you take an operating systems class. You look at the code that does this, in fact. So, summarizing our file system broad overview from the top, a disk is, without some organization on it, simply a large series of blocks of data that are indexable. To make it useful, we take either the entire disk or a portion of it, a partition of it, and organize it in what is called a file system. And a file system takes the data and disk and uses it for two broad groups of information. First, a set of inodes, that each one representing the metadata of a file. And second, data blocks that contain the actual content of the file. And the inode is the master information piece for a file, containing all its metadata and pointers to where its data would be on disk. Now, one comment I did make earlier I need to follow up on. There are various kinds of files. Obviously, files of an ordinary data type, and then directories are two that we've dealt with so far. But when you think about it, we've also designated or described keyboard and screen as files, and talked about the idea that that's a bit of a stretch, but when you think of it, they are either places you can read information from or write information to. In fact, every device attached to a Unix system is modeled as a file and has an inode. Now, it won't have data blocks if it's not a disk file, but there is nonetheless an inode for it, and the inode will have flags in it saying, hey, this isn't a disk file, this is a keyboard device, and perhaps a little more information about how that is attached to the machine and so forth. So the inode concept extends a little more broadly than just to disk files. Now, with inodes in mind, let's take a look at how a directory structure is organized. And I'm assuming, of course, that you're already familiar with the idea that there's a root directory in Unix. I've modeled it here, slash is its name, and has a couple of subdirectories, home and bin. And then here's a home directory with home accounts in it, and user home directories, one for C. Staley, one for J. Smith, and then some files inside of those, which we'll get to in a bit. And then I guess we also have bin, which has commands in it, as it does in a real Unix system, ls, cat, vi, ed, and a content file executable here that, again, we'll talk about. These are all set up to illustrate various ideas beyond just the straightforward directory tree concept. Now, we've said already that directories are files, and so they are. We've traversed such a file in the ls example done a little bit earlier, and the file content of a directory comprises pairs of name and a pointer to the file that is named. This is, again, reflective of what we saw when we did capital dir and dir entries in alt-ls. But the interesting question is, if I have a entry in a directory, let's do something simple to start with, like a file, my file here. If I have an entry, my file, in a directory, how do I point to where that file is on disk? And the answer is, all you need is an inode number. The inodes are in an array, and they have index numbers. And so the pointer to a file is an inode number. And that then leads to the inode on disk, which leads to all information necessary for the file. So I've drawn that abstractly here with an arrow to a file sample data, but the truth is that's really an inode number which would have sample data as inode and then sample data as inode, and term would lead to sample data as data. That core idea that an inode is how you get to a file, or an inode number at least is how you get to a file, is a central thing to understand. And interestingly, nothing prevents you from having an entry in one directory, maybe called prog1 in my home directory here, that points to or has the inode number of a file on disk, and another entry in a different directory, this one is the home directory for J. Smith, that has the same inode and points to the same file, even though it has a different name. This one is csprog, Clinton Staley's prog, apparently. You can arrange then for two different directories to have entries with different names in them pointing to the same file, translating that into inode terms, having the same inode number. In fact, if you notice, the inode doesn't include the file name. Files are not uniquely associated with names, as it turns out. They are uniquely associated with inodes, but you can have a file with two different names, prog1 in one directory and csprog in the other, and the same inode for each. There's a name for this, by the way. It's called a hard link. So let's drop that in there as a text term. Thus. And it even has an entry regarding it in an LS long listing. We've never talked in our discussions of LS about this column here. See how those little ones? They're almost always ones, but every once in a while you'll see one that's a 2 or a 3. And it indicates how many different directory entries are linking to that file. If you see a 2 here, that's a way of saying, well, you have this file as a.exe, but some other directory also is linking to that very same file, perhaps with a different name. The number of hard links to a file then. Typically one, but possibly more than one, as in our example here. So if we did an LSL, we'd see a 2 next to prog1 and a 2 next to csprog. Now, with the idea that directories are just lists of names and associated inode number, let's kind of go from the top here. The topmost directory in the entire file system is slash, or I should say in the entire directory tree. We'll get to the distinction between file systems and directory trees in a minute. Slash might have home and bin in it, and then those are entries with an inode number for the directory file. In the case of home, the directory file containing all of the home directories. Now, every directory has two entries, ... and dot in it. And in order to avoid being tedious, I did not show those in every single one of my directories here. You can imagine they are there. I showed them explicitly only in the home directory here. But let's be clear on what those are now. They are entries with the odd-looking names ... and an inode number that, of course, leads back to the parent directory. And dot is an entry with an inode number that leads, of course, to the very same directory we're currently in. But they follow the same pattern, names and inode numbers. They're just a little bit unusual in what inode they have. Now, of course, the /home directory has entries for further subdirectories and their inodes, and leading here and then ultimately down to individual files, as we already discussed. One interesting aside here, we've seen a case where two different directories have entries that point to the same file, that hard link. Can you do that with directories as well? Could I have, for instance, two different directories pointed to from other parent directories? Maybe I could have this directory here be both, or maybe this one here be both a child of home and then also be child of some other directory hard linked from two different parent directories. And the answer is no. You're not allowed to do that with hard links. The original Unix design did allow this. It turned into kind of a free-for-all graph. We think of directories in a tree-like structure, but nothing would really prevent us from having these entries with inodes pointing anywhere we like. We could make little rings of directories and arbitrary graph patterns of directories. And the original designers of Unix thought that would be kind of cool. And you could set up all manner of interesting relationships between directories. What they found out was that it was not kind of cool, it was kind of confusing. In fact, so badly so that they quickly ruled out having any kind of hard link except at the very leaf level, where a given file might appear in two different directories. You can set up hard links within directories, but you have to have special privilege to do so, and it's rare to see that happen. Now, is a single file system, or does a single file system contain the entire directory tree? No, as it turns out. If you think about it, a large Unix system has one file directory system, one root directory and everything underneath that. And yet, clearly it would have to have multiple disks. It's rare to have a single disk in a big system that contains every file. You need multiple disks. And a file system, a given file system, has to reside on just one disk. So, how do we take multiple disks, each with a different file system on it, and merge them into one grand directory? You know, for a counterexample, Windows, as anyone who uses it knows, doesn't do this. The way Windows deals with it is that you've got your C drive and your D drive, and you simply deal with different drives. It's not a unified system where the distinction between one disk and another is hidden. It's very obvious, and each disk has a letter. But Unix is not that way. And in fact, what happens is you may designate a given entry in a directory, and I'm doing that with bin here, as being the point at which another file system is, to use the Unix term, mounted. And this abstract diagram of the rectangle here is meant to represent all this stuff being on a different disk than all of this stuff, thus the label separate file system. So I could have a different disk with a file system on it that starts with a root that has what we would think of as the /bin directory, and then below that other stuff. And I can, with appropriate commands, arrange for the bin entry in my root directory to point to the root of this separate file system and effectively hang this file system as a branch of the overall directory structure. And again, the term there is mounting a file system. The advantage of this is that it all looks seamlessly unified to the user. You can be descending from root downward and cross from one disk to another as you go across mount points and not realize it's even happening. But it does have one significant drawback when it comes to this hard link business. The idea of having two different entries with the same inode number only works if inode numbers are unique. And within a file system, they will be. It's an array of inodes within a file system, and they are unique. But between two different file systems, they're not unique. So I can have an inode number 5 in file system 1 and an inode number 5 in file system 2, and they're completely different files. And when we have many file systems going on within the overall directory tree, that then means that I can only arrange this kind of hard link between two directories and a file that are all in the same file system. And if I want instead a link across to a file that's in a different file system, I can't do that by just giving the inode number. It would be ambiguous, and it would be presumed to be the inode number within my own file system, not the other file system, and thus not link correctly. Instead, there's an alternative, something called a soft link. And I'll drop that in here as a vocabulary term. A soft link is, in one sense, just an ordinary data file. But the data that it contains is quite short and is a text path that indicates some other file. And the inode for a soft link is specially labeled to indicate that it is that type of file, a soft link file. The result is when you try to open that file or interact with it in any particular system call, the system automatically, recognizing that the inode says it's a soft link, opens the file, reads the other file's name, and then goes to that other file and opens it for you instead. So you get this pointer effect from the soft link, and indeed you won't even realize that, for instance, my.vi, which is the entry in this directory that leads to this soft link, you won't realize that it's anything other than a direct link across to the vi file in bin, because if you try to open it, that's the file you'll get instead. You can't even see this content here normally. You can find it displayed in an ls listing, ls-l, if you arrange a soft link, and it will And we'll show you the arrow to the other file. Let me briefly illustrate how that might work. I'm in a directory here where I have a series of files related to one of the lectures, actually. And I'm going to create a copy of a file that is in a directory above and next door, /standard.io. And let's grab a copy of, say, transcript.a.html from over there. Now, I could do that with a copy command, but I'm going to do it instead with an ln command, which stands for link, -s, which is the option to say make a soft link. And then the rest of the command is exactly as though I were copying. So I'm going to take what I want to have, and copy that to the current directory. But what we'll discover is, while I get a copy that is transcript.a.html, and I can even look at it if I want to, and by gosh, there's the HTML, it is not actually a copy of the file in my current directory. Instead, if I do an ls-l listing, I get this funny arrow notation. And that's saying the entry that you have called transcript.a.html, it's actually a soft link file, and its content is /2studio/transcript.a.html, and that is why when you open it, you're actually going to get that other file instead. So there's a little more on soft links and how to set them up. There is one final point I want to get into here, just as an example of kind of odd things one can do with hard links. The entries vi and ed in the /bin directory, and this is the way they actually are in a lot of Unix systems, as you can see in my diagram, are both hard linked to the same executable. Now, vi is a command you should be familiar with from your Unix work. Ed, I would hope, is not something you've ever used. It is an even more primitive editor than vi, if that were possible. And in fact, it's the first editor that was commonly used in Unix systems in the 70s, and it was extended and modified to provide the full screen interaction that you get from vi. But there's one program that does both the ed, old-fashioned behavior, and the vi, at the time more modern behavior. And both these entries in the bin directory lead to that one executable file. So you get the same file, no matter which one you run. But it behaves differently. And the reason it does is that there is, of course, a #0 command line argument that is the command name used to start the program. And so the code for this thing checks to see if it was called vi or ed. And if it's called ed, it behaves in even more primitive fashion. And if it was called vi, then it behaves like vi. But hard linked to the very same file. And that's about it for our broad overview here. Be sure you understand the terms. File system, inode, data blocks, hard link, soft link, mounting, and then the broad ideas about file systems and inode numbers and so forth, and that a file doesn't really have a name exactly. It really is just a question of how it's called from whatever directory links to it. That the essential point is its inode number, not its name.